Hello everyone. After a long time, I am here with a video on material synthesis and characterization. Now, as I'm doing my PhD on the material chemistry, I thought I would give a brief outline about how it goes with the synthesis and what are the characterizations you have to do once you synthesize a material. Though you are not a material chemistry student, though you are not opting your PhD, even though if you are an organic chemist in PhD, you can have a look at this video and explain it to the others who are involved in the material synthesis. I'm sure it is going to help you somewhere, because the characterization techniques which I am going to brief over here can be used in any of the fields in your PhD. So before I begin, I would like to give an update on the Inspire Fellowship 12th advertisement. So it is being told that the results will be out till the end of the April, that is the last week of the April. Never it happened that the results have been so late. Usually it comes by the end of the December, but this time the results have been postponed to a very long time. I just request you to have some patience, because mostly the results will be out by the April. Then you can follow your further procedures for your final offer. So, talking about material synthesis, the basis of the material science is to study the structures of the material. The materials have got various structures and the properties are so different from one material to another material. So the basis is, once you synthesize a material, you have to study the structure of the material and try to understand the properties of the material using various characterization techniques. So if you have to synthesize some material, there are two methods. One is top down and another one is bottom up. The name itself suggests the top down synthesis. It means that you have to break up a large particle by use of some processes like ball milling, crushing and grinding, and break it down to a smaller particles. But there is some problem with this synthesis. It is that it can cause some crystallographic damage to the material which you have synthesized. Whereas the bottom up synthesis, it is like you are bringing all the atoms together and forming a molecule and then a cluster. That is, you are building up from an atomic scale to a molecular scale. It just refers to a build up of a material from the bottom, that is atom to atom, molecule to molecule, or cluster by cluster. Now this has the ability to generate a uniform size, shape and distribution. So logically you can just understand amongst these two why is this more preferred, because when you are trying to add few things together, it is very systematic, but when you break down something, the morphology is not in your control. It can really cause some damage to the crystal structure of the material. So there are various synthesis methods for the preparation of the materials. A few of them I have listed here, like hydrothermal synthesis, solvothermal chemical vapor deposition, thermal decomposition and pulsed laser ablation, combustion, gas phase methods, microwave synthesis and Sol-Gel method. So amongst all these techniques, the most versatile technique which is being used in the synthesis and which can be used in any of the labs in the whole world is Sol-Gel method. So I have worked on Sol-Gel as well as hydrothermal. So I'll brief you up only about these two methods. If you are interested to find out even about the other methods, I'll make a separate video on that. So Sol-Gel technique is actually a very versatile process for the synthesis of oxide materials. So let's say if you want to prepare any oxides like Cu2O, TiO2, ZnO, etc., SnO2, then you can use Sol-Gel method for oxides. For nitrites and acetates, you have to use hydrothermal synthesis. Acetates and nitrates, you prefer hydrothermal synthesis. Okay, we'll talk about these two methods. Sol-Gel method, it actually allows us to control the texture, chemical and morphological properties. Morphological, I meant the geometry of the material which you have synthesized. For example, I have synthesized a material Cu2O and graphitic carbonate, right? So if I put this material at 60 degrees Celsius, the morphology which I have got is cube. For 70 degrees Celsius, the morphology has been turned into star. Now your doubt is, what is so special about this morphology? What if it is a cube or what if it is a star? This we'll discuss in the characterization techniques. So for the lower temperature, let's say 80, 90 and 100, we use sol-gel methods. For higher temperatures, we go for hydrothermal synthesis. So this is actually, the hydrothermal synthesis is carried out in a pressurized vessel called autoclave with the reaction in an aqueous solution. The temperature in the autoclave can actually rise above the boiling point of the water. So a very high pressure is built up in this particular synthesis. So if, let's say, the temperature in the sol-gel method is 60 degrees, the same temperature if I maintain in hydrothermal, let's say if I have adjusted the temperature 60 degrees in hydrothermal, it won't be 60 in reality because of the high pressure buildup. The actual temperature inside would be roughly around 2 times of it, let's say 180 degrees Celsius. So actually it will be 180 in the hydrothermal. So it's a very high temperature, like high pressure maintained reaction, and it can be used to control the grain size, crystallite phase and surface chemistry when compared to the sol-gel. Whereas in the sol-gel, we can have a control on the texture, chemical and morphological properties. Now, once you have synthesized a material, even in the processing of your synthesizing, you have to take care of many things. I will explain it in some other video. So now I will be talking about characterization techniques. So the very first characterization, wherever you are in the world, if you are synthesizing a material, you will go with the powder X-ray diffraction studies, that is PXRD, powder X-ray diffraction. So this is the first confirmation of the composition of the material. If your material is formed or not. I wanted to synthesize Cu2O, Gc3N4. Was I able to synthesize it? Is it formed or not? The peaks of Cu2O, the peaks of Gc3N4 in the XRD confirms the formation of the material. Let's say Cu2O has some peak around 36 and graphitic carbon nitride individually it has peak around 14 and 27. Now these are individual XRDs of Cu2O and graphitic carbon nitride. Now what should happen in the composite is that the peak should be somewhere above or below the 36 value, and the same with graphitic carbon nitride. Let's say 14 was the actual peak, your peak should be either above or below 14. The same with even 27. It means there has to be some shift in the peak position if a composite is formed. Let's say if the composite is at same value, Cu2 was 36 and you got again a peak at 36 and 14 and 27, that means that the composite has not formed. There has to be either left or right shift when a composite is formed, and that is confirmed from the powder X-ray diffraction. So once you confirm that your material has formed or not, then you go for morphological studies, that is scanning electron microscope, SEM studies will tell you about the morphology. So in the SEM, it creates an image by detecting reflected or knocked off electrons. So yeah, as I told, this particular material I have synthesized at 60 degrees Celsius, and from the SEM studies I have come to know that this material is in the form of cube with some dots on it. Now this dots means porosity. The porosity in the material is being confirmed. Yeah, the porosity in the material and the size of the material, the size of the molecule is being confirmed using SEM studies. Okay, I was little distracted. Fine. The porosity of the material actually plays a very important role in determining the application which you have to further do for your material synthesized. For example, pure Cu2O is a plain surface cube. You won't find any pores on it, but if I add graphitic carbon nitride to it, some porosity is formed on the surface of the cube which can be observed from the SEM. Okay, so this porosity plays a very important role in the application when you are going for the application studies. Energy dispersive X-ray analysis, that is EDAX. EDAX is going to tell us what all are the elements present on the surface of the material. So this was a bulk technique, whereas SEM is a surface technique. So what are the elements present on the surface can be confirmed using energy dispersive X-ray analysis. But there is a problem with EDAX. There are elements like lithium, beryllium, helium which cannot be detected using EDAX. So what is the characterization technique which we have to use? If it is not been detected here, we'll discuss further. So once you confirm the morphology and the material formation, now you have to go for the techniques which are going to help for your application. Okay, so FTIR studies is anyways a common technique. We will determine what are the functional bonding groups which are present in your material through these studies. Now let's say you want to have an application of photocatalytic studies. Well, so if you want to do photocatalytic studies as your application part, you will choose only optical studies for the confirmation of the material, not the thermal studies. If you have to do gas sensing experiments, let's say gas sensing, you want to perform gas sensing experiment as your application, then you will be going for the thermal studies but not optical studies. So based on the application which you want to do, you have to choose your characterization techniques, but these are common everywhere. Okay, so optical studies, in that we have UV-DRS studies, that is ultraviolet diffused reflectance studies. This is done to find out the band gap of the material. Let's say if your band gap is in the visible light, which you determine UV-DRS studies. So this is very helpful for the photo degradation studies. Okay, for the photo degradation studies, if you want to degrade some dye, it is always better if you have the light in the visible region, because UV region, it is harmful and it is not a natural source available for us. So what is the only natural source we have is sun, which is a visible light. So it is always better to get a band gap of a visible light. In the sense, if it is not in the visible region, you can fine tune it using the doping or various other techniques to shift the band gap from the UV to the visible region and then perform the degradation studies. So you do PL studies, that is photoluminescence studies. This is used to calculate the lifetime of the electron which is sitting in the excited state. The more is the lifetime of the electron in the excited state, the better will be the photo degradation studies. So that's how you have to choose your characterization technique based on the application. Let's say if you are doing gas sensing application, you don't need the optical studies, right? This is not going to help anywhere. Instead, you have to measure the TGA, DTA and DSC are the techniques you have to perform before you go to the gas sensing experiments. Well, now why do you have to do TGA? TGA is used to determine the thermal stability. In the gas sensing experiments, we go to the, we use temperature as one of our parameters for studying the sensing performance. So to find out the thermal stability of your material, you first perform TGA. Let's say this material is stable only till 130. How do I know it is stable only till 130? Using TGA. Once I know it is only till 130, whenever I do gas sensing experiments, I'll go only till 130. Beyond that, I won't go, because there is a possibility, it's not a possibility. There actually what happens is Cu2O gets transmitted to copper oxide. It gets converted to copper oxide. That is, oxidation takes place. So the whole material properties will be changed if it is +2 to +1. Okay, and you do also DSC. DSC is done to find out the melting temperature, heat of fusion, latent heat of vaporization, as well as glass transition temperatures. So you do the thermal studies if it is gas sensing experiments, and if there are any other applications, if you want to do let's say you want to make a polymer and all, then also you have to go for thermal studies. Okay, there also you determine what is the thermal stability of your material. Okay, so depending upon the application, you choose your techniques. Apart from these two, there is a technique called BET. This we have already studied, Bronner, Emmett and Teller studies. This will give us the pore size of the material. Pore size and surface area can be determined using these studies. Now this is a very important characterization technique which has to be performed, because for applications like photocatalysis and gas sensing, the more is the surface area of the material, the better are the properties of the material. The high activity of the material depends upon the high surface area. Let it be photocatalysis or as well as gas sensing. So you determine that surface area as well as the pore size of the material using your BET studies. Now XPS. Now I have told here that EDAX cannot detect elements like lithium and helium, beryllium. Now this can be detected using XPS. XPS is also used to confirm the composition and the various oxidation states present in the sample can be confirmed using XPS. Now these two characterization techniques are always preferred to be done in the last, once you are done with all these techniques, because XPS provides lot of data. So if you do XPS for 6 to 7 samples and later sit and try to analyze it, you will get confused totally. So my guide always asks me to do XPS and TEM. Once you confirm all the characterizations, once you do your even application part, and then we have to do the XPS technique, followed by TEM. Now TEM is transmission electron microscopy. SEM and TEM, what is the difference? SEM creates an image by detecting reflected or knocked off electrons, whereas TEM, the transmitted electrons which are passing through the sample to create an image is what obtained using TEM. Okay, so TEM offers a valuable information on the inner structure of the sample, such as crystal structure and morphology, which is not the same with SEM. SEM only the surface morphology and the surface information, whereas from the TEM the inner crystal structure can also be determined, and it is very well-known technique for finding out the particle size to the nearly 1 nanometer can be detected using TEM. Well, okay, so TEM can be used to determine the particle if the size of the particle is almost less than 2 nanometers. And the another point over here which we have to notice is that you can perform TEM only if the particle size is very small, let's say less than 150 nanometers. This is not the case with SEM. You can perform SEM even for the microns, but for the TEM you have to have the particle size of less than 150 nanometers. It is a sophisticated technique, and the sample preparation in the TEM is really difficult when compared to the SEM. So you cannot have 10-15 samples for XPS and TEM. The best sample, the optimized sample has to be chosen and given for this XPS and TEM characterization, whereas other characterizations are little simple. So this is all what I wanted to share, like what I have learned in my PhD in these 2 years. And if you want me to explain any of these techniques in detail, or any other thing which would be helpful in your research, you can let me know. I'll start making videos even on the research side other than for the CSIR techniques. I also request you to please lock down, sit at homes, have a good diet, read books, enjoy music, spend time with the family, don't go out, even teach others not to go out, because this is really a tough time for the whole world. So let's lock down and enjoy the free time with the family. Thank you.